We'll bring back my favorite student, not Grant. Here we go. Question wants me to find impulse. Well, impulse is another word for change in momentum. There's two ways I can do this. I can either go force times change in time, or I can go final minus initial. Which one's right? Well, I look at what they gave me, and I notice I don't see a force or a time. I think I'm going to go final minus initial, which is going to be mv final minus mv initial. Now, it looks like it says bring him to a stop. I think the final momentum is 0. The initial momentum is going to be mass times velocity. And I'm going to get negative 448 kilogram meters per second. If you got that 2 out of 2, otherwise I would probably go half mark for that, half mark for that, half mark for the numbers, and a half mark for the answer. Yeah. I'm going to give you 1.5 out of 2. Because this person has to lose momentum. You have to take momentum away from the runner to bring them to a stop. Number 2, what is the magnitude? Now, Rachel, since number 2 only asks for magnitude, I guess if you botch the sign for number 2, I'll still have to give you grudgingly full marks. Anyways, needed to change the speed of a 10 kilogram body from 20 meters per second to 12 meters per second in a time of 5 seconds. I am going to get a negative answer here because I'm slowing it down. It is going to lose momentum. I've got to take momentum away from it. They want the impulse. Impulse is going to be final minus initial. Wait a minute, Mr. Dueck, why didn't you go force times time? I see time there. Yeah, I do too, but I don't see force there. And in fact, I notice part B says find the force. So I said, oh, I bet you they gave me the time so that once I find the impulse, I can find the average force. It's going to be mv final minus mv initial. It's going to be 10 times 12 minus 10 times 20. I think your answer for part A is going to be 120. Take away 200. Do you get negative 80? B. What force is needed? Well, force is impulse over time. Not momentum over time, change in momentum over time. So it's going to be negative 80 over 5. It's going to be, now technically it's negative 16 newtons. Is that right, by the way? I won't be fussy on the negative because for part A I said magnitude. What the negative here is giving me is a directional component. It's saying, look, whatever direction this object is traveling, if you want to slow it down, the force better be in the opposite direction. Okay? 2 for each of those. Rachel seems pretty thrilled. Happy New Year. Number 3. A car, blah, blah, collides. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. Before the collision, what's moving? Mass 1, mass 2, or both? Wham! They collide. After the collision, what's moving? Mass 1, mass 2, or both? Elastic or inelastic? This is an inelastic collision, stuck together. So it's going to be momentum. And now I pause. Does this question mention any angles, any north of south, any? Oh, so I don't need to dolp here, Emma. I'm not going to be adding vectors tip to tail. I can just say let to the right be positive and to the left be negative and be consistent. Oh, thank God. M1 V1 initial equals M1 plus M2 V final. No need to go all vectory, no need to go all tip to tail, no cosine law, straight high school algebra. The only issue is, and I am going to give you some stuff in a straight line on a test, but be careful. If it does change direction, make sure you let one direction be positive and one direction be negative. So especially if it bounces off a wall or bounces off the ground or what goes up must come, or something like that. I guess V final is going to be M1 V1 initial all over M1 plus M2. It's going to be 3.2 times 1.2 all over 3.2. Don't know why I put brackets there. That's 3.2 plus 1.6.8, Mr. Dueck. Do that one in your head, Mr. Okay. I think I can. It's going to be 16 times 12. 16 times 12, 144 plus 48 is going to be 1.88? No? 2.04? I'm off. Dueck. I'm not even close. Maybe I'm off by a factor of 10. I might have missed the decimal. 0.76. Wow, Dueck. Yes. Geez, it's 188 divided by 2. Yeah. Had a chance to show off and I blew it. If you got that, 4 out of 4. Otherwise, I'd probably go 1 mark if I saw that, 1 mark if I saw that, 1 mark if I saw that, and 1 mark for the answer. If you could give yourself a lovely score out of 10, please. I think I told you before Christmas, actually momentum and the previous unit, work and energy, on the curriculum are part of one big uber unit called conserved quantities, because there's the law of conservation of energy and there's the law of conservation of momentum. Momentum actually is handier looking at collisions, but it's trickier because it's vector math. Conservation of energy is a scalar, it's nicer, but it's actually not as flexible in some ways. But there are some cool questions that involve both. And the first is what's called the ballistic pendulum. So here's what I wrote. Problems involving momentum and energy. Problems where there's a collision and a change in height, change in speed, yucky, curvy path. Stuff to keep in mind. We apply momentum to collisions or explosions. We use energy to analyze pendulums and curved ramps, change in height, change in speed. And for a really, really complex problem, you want to break it down into steps. Usually what I do is I kind of divide my page into little columns or something like that. So here is the first one. This is the ballistic pendulum. I don't know if you watch crime shows like Law and Order or legal shows, but one of the things that they use in the courts of laws is they use ballistics. They'll tell you where a gun bullet came from, and one of the great ways they do that is they can then figure out how fast the bullet was traveling. And they do that now. We can measure bullet speeds using radar. What did they do before we had radar? Because we only invented radar around World War II. What did they do 100 years ago? How could they figure out how fast a bullet was traveling? It's not like you can time it with a stopwatch. Human reaction time isn't that fast. So what they did, they were very clever. They used this thing here called the ballistic pendulum. We're going to do this going forwards, and then I'll show you how going backwards you can use this to figure out how fast the bullet must have been traveling. Here's what it says. We're going to shoot a bullet, and it's going to hit a pendulum, a block of wood, and it's going to stick inelastic. Well, I think when the bullet hits the wood and they stick, the wood's going to swing up and then come back down. It's going to swing on a yucky, curvy path That part is conservation of energy. But when the bullet hits, there's going to be a collision. And what this question asks is, find the height h, find how high the pendulum is going to swing up. Can you see, Marissa, we do have a collision and a change in height curvy path. So what I'm going to do, and what it says here, is the solution, we need to recognize there are actually two events, the collision and the swing. I'm going to divide my page in half. What are they wanting me to find? The final height, the swing. Well, that's a curvy path. That's a change in height. That's a job for conservation of energy. Did I hear a phone? I heard Siri, I think, coming from over that way. Jake's looking a little sheepish. Grant's looking a little sheepish. It was you? So maybe flip it so that the switchy thingy's on vibrate or something, or off? First thing Monday, assuming Grant is on time. Okay. Are any of these zero? Is the initial speed after the impact of the bullet when it starts to swing zero? Well, no, because otherwise it wouldn't swing at all. Is the initial height zero? You know what? We said the nice thing about energy is we can put a height of zero wherever we want. Let's pretend the bottom of the rope is zero. At the top of the swing, how fast is it traveling? Ah, that's zero. At the top of the swing, is it on the ground? No, so final potential is not zero. So we end up with this. A half m v initial squared. Now, this m is the mass of all of them because they're stuck together after the collision, equals mgh final, where this m is the mass of all of them. Although, wait a minute, I guess I didn't need to be so fussy about the masses. Much like on amusement park rides, it turns out. And they said, find the final height. Okay, Logan, I guess the final height is going to be v initial squared divided by, move the g over by dividing. You okay with that, kiddo? Cool. Do I know g, 9.8? Do I know the initial speed after the collision? Not yet. After the what? Hey, that's a job for conservation of momentum. Before the collision, now normally, by the way, I'd use B for bullet, but it's also B for block. So I'll call the bullet mass 1 and the block mass 2. Just like reading from left to right, like we've kind of always done. So before the collision, what's moving? Mass 1, mass 2, or both? Momentum of object 1, initial. Bam! They collide. After the collision, what's moving? Mass 1, mass 2, or both? Stuck together or separate? Look at the picture. Are these in a nice straight line, or are there yucky angles? In the collision portion, nice straight line. In the scalar portion, who cares? It's a scalar. In other words, I don't need to draw vector triangles. By the way, I could, and in fact, later on in the notes, you're going to see I put a couple of scholarship questions, but I have a feeling I'm going to skip those in the interests of time in this lesson so I can show Vanessa the final 10-minute explanation of the bullet block video and fit that in. But we could. That'd be overkill. That'd be, again, beyond my A+ level of a question. Okay? Momentum is mass 1 v1 initial equals m1 plus m2 v final. where I think Kyle, this V final is V initial after the collision when they move up. We've seen this before, Ty. We've looked at situations where there was a before and after, and the final of the before became the initial of the after situation, right? Yeah? Hey, Ty, how would I get the VF by itself there? And why can I do that? It's a nice straight line. You were away yesterday. Make sure you watch the video lesson. But those of you that were here, hey, as soon as there's angles, we're looking at 7, 8 lines of work of, drawing and lots. So here we kind of smile and say, cool. So Ty, you're saying V final after the collision is going to be M1 V1 initial divided by M1 plus M2. You'd be saying correct. Which is going to be, what did I say the mass of the bullet was? 20 grams. Careful, what's that in kilograms? Don't say 0.2 because it's not. 0.02. Its initial velocity was 100, which is slow. 100 meters per second, that means it crosses a football field in 1 second. You could actually follow that with your eyes. I stole this diagram from somewhere else, and the only thing I don't like about the diagram is that initial value. But the rest of the diagram looked great, and I don't feel like redoing it just for that one value. Divided by 0.02 plus, what was it, 4 kilograms? So after the collision, how fast do they move off at? 0.02 times 100 divided by, well, 4.02. I think I can add that in my head. Move off at, you guys get 0.4975, blah, 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 blah. And since this is my final answer, I'll carry a few extra sig figs. I'll go 0.49751. Which means over here it's going to be 0.49751 squared all over 2 times 9.8. Rachel's looking puzzled like she didn't get the 0.49.
Yeah, for VF, I got 0.476.
Am I wrong? Did you guys get this? Is this right? Did you put the bottom in brackets, Rach?
Yeah, I did.
And you went 0.02 times 100? Don't clear anything. I'll come look. So now I'm going to go squared divided by 2 times 9.8. And you get a really small number because this bullet is traveling really small. This block moves up 0.126 meters, which is like 1.3 centimeters. It moves up about that much, which is a bad value, okay? But I'll commit to it. Final height equals 0.0126. That's 3 sig figs. That's 4 sig. No, 3 sig figs. Yes, it's 4 decimals, but it's 3 sig figs meters. Here's what I want you to notice. Put your pencils down for a second. I said this is how they used to figure out how fast the bullets travel. What they used to do is they would do this experiment and they would measure the height with a camera, because film has been around for quite a while. You could do it with strobe photography. So if you knew the height, because you'd measured it, if you knew the height, could you figure out the velocity after the collision? Yeah. If you knew the velocity after the collision, could you figure out the velocity of the bullet before the collision? Divide by the mass of the bullet. That's how it was done. And then you had your rifles, your bullet speeds, your ballistics. It's called the ballistic pendulum. I'm going to say I like that question in that on your test, there's definitely going to be a question that has both momentum and energy in it. I will guarantee that things will be in a nice straight line for the momentum portion. In fact, I'll even guarantee they won't be in a nice straight line for the work energy portion, but what do we care? It's a scalar. Example 2. If mass 1 and mass 2 and mass 3 are all 4 kilograms, And mass 1 has an initial velocity of 32 meters per second. Find the final speed of mass 3 if the height equals 0.82 and all collisions are hit and stick. Fancy word, inelastic. Okay. How many collisions are there in here? 2. So there's going to be 2 different momentum equations. How many changes in height, changes in speed, curvy paths are there? So I think I'm going to do momentum twice and then conservation of energy once. But aside from the energy part, everything else is in a nice straight line. No vector triangles or stuff. Cool. Maybe. If M1 equals M2 okay. I'm just puzzling right now. Let me pause the video. I think what I'm going to do is I'm going to, in the interest of time, skip this one. And I'm going to do the roller coaster. Why? Because I like this question. I like this question. I like this question. It's a roller coaster. Mr. Dueck, where did you find that beautiful diagram? You must have scoured the internet. Someone's got some real artistic talent. Why, thank you. Thank you. Okay, this is my attempt at drawing, and yeah, it's always bad. Okay. A roller coaster with an initial velocity of 8.6 rolls down a track with a height of 18 meters. It strikes a second identical roller coaster. They each weigh 250 kilograms. And it has an initial velocity of 2.4 meters per second. Coasters stick together and continue up the next hill. How high can the other roller coaster reach? Cool. This question has, I think, 3 parts. Don't write this down. I'm going to really gum up my diagram. Change in height, change in speed, yucky curvy path. I think I'm going to do conservation of energy there because at the bottom of the hill it's going to be going faster. Collision. This is a job for conservation of momentum. Change in height, change in speed, yucky curvy path. Conservation of energy. Is that okay? Question, kiddo? Oh, okay. You're all looking at other stuff? Is that all right? Did I give you guys the whole page? So instead of me doing this, breaking it into columns this way, I think I'm just going to do the first, second, and third. I'm going to do everything horizontally, I think. So I'm going to call this situation 1, situation 2, situation 3. Something to be organized. Situation 1. Tie, curvy path, change in height, change in speed. Does this question mention heat? No? Okay. Are any of these 0? I'm ending up on the ground. Common mistake kids make is they do that. No. Is it starting at rest? So I can't say that. So I'm going to get this. A half mv initial squared plus mgh initial equals a half mv final squared. Hey, there was stuff like this on the test. This is almost like going over the test without actually going over the test. Oh, ha. What I want to find is how fast it's going at the bottom of the hill, because it's sped up. I'm going to go times by 2, times by 2, times by 2. That cancels. That cancels. In fact, I get that variation of VF squared equals VI squared plus 2AD that came out of conservation of energy. I get VF squared equals VI squared plus 2GH, which is really plus 2AD. Oh, how to get rid of a squared? I'm going to get the square root of 8.6 squared plus 2 times 9.8 times 18. At the bottom of the first hill, this roller coaster is going to be traveling 8.6 squared plus 2 times 9.8 times 18 square root. Do you get 20.6581703? I'll just wait and see if Rach gets that too. Grant might even get his calculator out one of these days. No, wait a minute. He's got a brain. He's using that instead. Is this my final answer? No, I'll carry some extra sig figs. I'll go 20.6582. Check. Situation number 2. They collide. Did I say collide? Well, you know what that's a job for. Before the collision, what's moving? Mass 1, mass 2, or both? Both! Oh, the second car wasn't stationary. Oh yeah, I can see that from that wonderful diagram that Mr. Dueck drew. There's a little V there. Whew. So I'm going to have momentum 1 initial and momentum 2 initial. Knock, knock. Wham! They collide. Right? After the collision, stuck together. Momentum both final. Got to make sure. Am I going to have enough room? Yeah, I might have to do the rest over. Okay, we'll figure it out. So this is going to be mass 1 V1 initial plus mass 2 V2 initial equals M1 plus M2 V final. And what I'm trying to find, Logan, is this bad boy right here, V final, after the collision. Look at my wonderfully drawn picture. Does it offer the suggestion of any angles, any vectors here, any yuckiness on the collision, or is it in a nice straight line? Oh, so to get the VF by itself, just divide by M1 plus M2, right? VF is going to be M1 V1 initial plus M2 V2 initial. But by the way, look at car number 2. Which way is it moving, to the right or to the left before the collision? What if I'd had it moving to the left? How could you deal with that in this equation? What would you have done? You just made the velocity a negative. That'd be kind of cool. Be pretty catastrophic, colliding like that, but kind of cool. Divided by so V final is going to be mass 1. Did I say they're 250? 250 times 20.658 plus 250 times 2.4 divided by, Rachel, I added 250 plus 250 in my head to get a 500 on the bottom there, okay? Oh, more than one number on the top, brackets. 250 times, hey, answer button, plus 250 times 2.4 divided by 500. 11.52908. I'll go 11.5291 because this is not my final answer yet. And that's meters per second. Well, it looks like I'm going to do the rest kind of in this area here, in my high-tech spacing. Part 3. Hey, there's a change in height, there's a change in speed, there's a curvy path. Okay. Oh, are any of these zeros looking in situation 3? You may find that that wonderfully drawn picture offers you some assistance in figuring that out. Sorry? Oh, once again, you're down on Prince Edward Island? PEI, okay. Carly says PEI is nothing. Nothing. What else? At the top, for a split second, we come to a stop. Oh, this one's not too bad. In fact, this is very similar to the ballistic pendulum, I think, that we just finished. It's going to be a half mass of both V initial squared equals mass of both G H final. Mr. Dueck, why are you emphasizing that it's a mass of both? Before Christmas, on the Monday video lesson, we did do one where when we were finding the total loss in kinetic energy for part 1, it was the mass of 1 because only one object was moving, but for part 2, both were moving. We had to take that into account somehow. But here, yeah, the masses cancel. Final height, VI squared over 2G VI squared over 2 times 9.8. You get 6.78? Okay. Hey, that's a nice question. There's some physics 12 in there. We're combining momentum and energy. But the nice thing, oh, and it's a curvy path. But the nice thing is, truthfully, Ty, most of the actual sub-physics is physics 11. Straight lines. No big vector dealies. Okay. But really, that's what's going on in this little toy. Turn the page. Football. So for my football players, a 100-kilogram fullback, I made a nice round number, is running with a football at 2 meters per second. He is met head-on and sticks inelastic to a tackler. Which tackler is more likely to stop the fullback? A 200-kilogram lineman moving at 1 meter per second? A 50-kilogram cornerback moving at 4 meters per second? Or both the same? And convince me. What do you think? We have a 100-kilogram fullback running at 2 meters per second. He gets hit head-on. I did head-on on purpose so we didn't have to worry about angles. Which is more likely to stop the fullback? A 200-kilogram lineman moving at 1 meter per second? Or a 50-kilogram cornerback moving at 4 meters per second? Or both the same? Grant, what do you think, football boy?
I'm saying both the same.
Convince me.
Because
Okay.
well, like, momentum's like the same, both of them.
First of all, there's 3 different things. So when you say both, do you mean both the lineman and the cornerback? Or are you talking both the tackler and the full? I'm not sure what you mean.
Like,
First of all, you know what? How much momentum does the fullback have in your head? How much momentum does the fullback have in your head? Can you go mass times velocity?
200.
Okay, so the fullback, let's call it momentum F for fullback, has 200. If we want to bring him to a stop, Rachel, what impulse do we have to give him to bring him to a stop? I'll give you a hint. Negative how much exactly?
200.
Negative 200, okay? So what we need to stop, we need an impulse of negative 200 kilogram meters per second. Okay, how much momentum does the lineman have? How much momentum does the cornerback have? So do they each have enough momentum to cancel out the momentum of the runner and end up with a net momentum of 0, which, by the way, is the final momentum of every tackle, I think? Yes? So both the same. You watch football? You watch football? So here's my next question, my follow-up. Why is it then, or which tackler will cause more hurt? Okay. You watch football? What are the biggest hits? What are the biggest tackles? What are the most spectacular hits delivered by? Big, fat, slow linemen? Think about some of the biggest hits that you've seen. What positions deliver them? Linebacker, cornerback, safeties, the smaller guys, not the bigger guys. Why? Well, Rachel, you're right. Hurt is not momentum. Hurt is how much energy you have to absorb. So now what we want to ask is, even though these guys have the same momentum, who has the most kinetic energy? The kinetic, let's change colors, Mr. Dueck. The kinetic energy of this lineman is a half mv squared. It's going to be a half times 200 times 1 squared. Grant's got his brain, no calculator. He can probably do that in his head. What's 1 squared?
1
Times 200.
200.
Half of that. So this lineman has 100 joules of kinetic energy, and he's going to pass that on to the person he tackles. What about this cornerback? The kinetic energy of the cornerback is going to be a half mv squared. It's going to be 0.5 times 50 times 4 squared. Grant's still feeling pretty good. He can do this in his head. Grant, 4 squared.
16.
What's half of 16?
8.
8 times 50.
400.
He has 4 times more energy to pour into that person who's getting tackled than the lineman. And the worst, so the faster you're going, now it is true though, there is an M in the equation as well. And so if you have more mass, that also delivers more hurt. The worst collisions are when you get those freaky linebackers that have cornerbacks. Well, you know what? It's the safeties. They're the best balance between almost cornerback speed, but they usually have about 20 or 30 pounds more than the cornerbacks. They're the ones that deliver those crazy open field, holy smokes, hits, right? So, cornerback transfers more energy. By the way, then, football guys, going back to part A, if you're heavier, you don't have to be moving as fast. And this is why, and I think I've said it before, but I'll say it again. In the NFL and then in the pros especially, a lot of those defensive linemen, those, you know what, as long as I don't lose too much speed, maybe it's worth putting an extra 20 or 30 pounds around here. It's not that they're fat and out of shape, although some of them are. They're not out of shape. They realize that fat is that extra mass is an asset. It's an asset. It's also why you look at the cornerbacks. They've got very low body fat because they want muscle mass to help their speed, but otherwise you want to be quick. Okay. Homework. Number 1. What's 1B asking me to find? Work. I think after you do the collision, work is going to be the change in potential, 0, plus the change in kinetic. Okay? 2. 3 is good. 4 is good. Ooh, 4 requires some projectile motion. 5 is good. Sure, it's actually, 6 is good. 7 I'm going to pass on. 9 is good. Whew, 10 is tough. 11 is tough because it's got 2 yucky angles to deal with. No, 3 yucky angles to deal with. It's doable, but it's pretty yucky. Well, 12, though, for baseball players. Okay. I haven't taken questions on the angled stuff yet. Please be honest. Who has finished lesson 6 from before Christmas? That was the first one, okay? And who has finished lesson 6.5 from last day? Can you try and, honestly, all of you, get them done for Monday? What I'd like to do, this was my sense. I had a feeling people have not wrestled with the angle crashes, and they're nasty. On Monday, I will start out saying, hey, questions from lesson 6, from lesson 6.5, and lesson 7, but get caught up. So you have 25 minutes, but of course Vanessa wants me to show a video.